In this lecture, we are going to solve this problem called clone graph. It is a very famous problem on graphs from Leetcode. And in this, we are initially given a graph data structure and a starting node. And what we have to do is we have to create a new graph data structure that is similar to this given graph. Okay, so all the nodes which are in the provided graph, or you can say this is our old graph, they should be there in our newly created or the new graph. All these nodes should be there, and all the neighbors should be also the same in the new graph. We have to create a deep copy or a clone for this given graph. Okay, so how can we do this? So in firstly, we have to create a new graph. So we will create a data structure. We will use dictionary to create our new graph. And in the dictionary, what we will be doing is that we will keep the keys as references to the nodes in the old graph, and their corresponding values are going to be the newly created nodes. So I'll explain that later. What I mean by that is, and what we are going to do is we will be traversing through this old graph. Okay, so that will just give us information about what the different nodes are and what their neighbors are. Okay, so we will be traversing through the old graph, and uh, along with that, we will also keep on updating our newly created graph. For example, I'm traversing the old graph and I'm on the node 2. Then I see that it has neighbors 1 and 3. Okay, so in my newly created graph, I'll make sure that there is node 2, node 1, and node 3, and I'll add node 1 and node 3 as neighbors of node 2. Okay, so this is what we have to do. Now, initially we have this simple graph. Okay, so here it is given in the problem. We have node 1, and node 1 is our old node that has neighbors of node 2, node 3. Okay, and node 2 has a neighbor node 1, node 3. Similarly, node 3 has a neighbor of node 2 and node 4, and node 4 has a neighbor of node 1 and node 3. Okay, so this graph is also in the form of a dictionary where the key is actually the reference to a given node, and the value is actually the node instance. Okay, so if you know about the class and instances, so we have the node class, and an object of the node class is the value in our dictionary, and this key is just the reference. Okay, so the key is the reference for that particular node. So what we will do is we will create a new graph. In this new graph, we will be reusing these same keys. We will keep our key as reference to the old nodes, but since we have to create a new graph, what we will be doing is the corresponding value for the node are going to be new node. They are going to be newly created node instances instead of referencing or giving any of these old instances. Okay, so let's see how we are going to do this. So let's start doing DFS in this graph. Since we will be doing DFS, we will be able to traverse through the complete graph, and we will know that what the different nodes are and what their neighbors are, which we need to know so that we can create a new graph, right? So we are starting from node 1. Okay, so in our new graph, we have to add node 1 firstly. It should be there, and node 1 we have added in our new graph firstly. Okay, since we are doing DFS on this graph, and currently we are on node 1. Okay, so we have first thing we did is basically we have added an entry in our new graph. The key is just the reference to the old node. Okay, in the old graph, and the corresponding value is a new instance for the node with the given value of 1. Okay, so we have created this new node. Now what we need to do, we have to mention that node 1 has neighbors as node 2 and node 4, right? And node 2 and node 4 are going to be references within the same graph. So that means node 2 and node 4 must exist, right? So we are going to add new node 2 and node 4 also in this graph when we are at the first starting point. Okay, we also added these two. Why? Because they are the neighbors. And then what we need to do, we need to provide that node 1 has neighbors node 2 and node 4. Okay, so we have set the node 2 and node 4 as the neighbors. So now we are done for node 1. Okay, now we will do DFS and move to the next. In the DFS traversal, we will move to the next node, which is node 2. Okay, so on node 2, we have node 1 and node 3 as the neighbors, and node 2 is already there in our new graph. Okay, node 1 and node 3 should also be there. No, we know that node 1 is there, but node 3 is not there. So what we are going to do, we are going to add node 3. Okay, now since we have node 1 and node 3, we are going to give the information that node 2 has neighbors as node 1 and node 3. Okay, so node 2 neighbors will be updated as node 1 and node 3. Okay, so on 2 our DFS is completed. The whole algorithm is not completed, but for 2 the traversal is done. Now we have to move to the next node, which is the node 3. Okay, so on the node 3, we know its neighbor are node 2 and node 4. So node 2 and node 4, they are already there in our graph. We do not have to create new node. And node 3 is also there. We also do not have to create new node. So simply what we can do is we can update that node 3 has neighbors as node 2 and node 4. Okay, so now we are done for node 3. Okay, we have a node 3 entry in the new graph, and we have its neighbors as well. Okay, so we will move to the next one, which is 4. Okay, so node 4 also exists already. Okay, node 1 and node 3 also exist already, so we do not have to create them as well. So one only thing we have to do now is we have to tell that node 4 has node 1 and node 3 as its neighbor. Okay, so for the node 4, its neighbors are going to be updated to node 1 and node 3. And like this, we have built our new graph. Okay, so this was the solution. We have to, we are using the same references. Okay, the one that is given to us in the question. In the question, we will be giving an starting point, and we will use the same node references which are given in the problem, and the correspond as the key in our new graph data structure, which is a dictionary, and the corresponding value will be a newly created node. Since we want to clone the graph, we will be creating new nodes instead of reusing the older ones. Okay, so let's just code solution to this particular problem. So what we need to do is we need to do DFS from the starting point, which is given by the variable node. So let's first check if not node, if it is none, then simply just we can return none. Okay, otherwise what we need to do is we have to perform the DFS. Okay, so within the DFS, we will be firstly, what we will be doing, we will be providing the node. Okay, and one thing that we will also need is basically we will need a graph data structure, our new graph. Let's call it new graph. Okay, and it's a dictionary. So like this, we can give the graph data structure, and we can also provide a visited set. Okay, that will keep track of the nodes that we have visited, so we do not revisit any nodes in our DFS algorithm. Okay, let me just maximize the screen so that we can focus more on code. So visited is our newly created set. Okay, after this DFS, we will have our new graph. We will have our new graph completed. Okay, new graph will have all the nodes from the old graph. And what we need to do, we will just return the new graph starting point, which will be given by new graph, and node is the key. Since we are using the same keys as the old graph has in our new graph. Okay, so let's just also implement this our DFS, that is not only for traversing the whole graph or given graph, but also creating new nodes that are part of the new graph. Okay, so in our DFS, we will be given this, and then we will be given a node, or you can say, let's just call it node only, and we will be given a graph. Okay, so I'll call it new graph. So that we do not get confused between new and the old graph. Okay, and we will be also having the visited set. Okay, so if there is not node, then you can simply return there is nothing to traverse. Otherwise, what we are going to do, we are going to set add the current node to visited so that we do not revisit it. Okay, so when we are doing this, we are visiting the current node, we have to also ensure that this node is there in the new graph. So if node not in new graph, then what we are going to do, we are going to add it. New graph node is equals to node, and let's this is going to be not.well. Okay, so we know when we were doing this algorithm, then what we were doing is, firstly we will when we were doing DFS, we were firstly creating the node that we are currently on. Okay, if it is not there, and then what we will be doing, this will be marked as visited. The current node will be marked as visited. If it is not there, then we have to also add it into the new graph. Okay, so now what we need to do is we have to check for its neighbors. Okay, so in this code, how we are going to do is for neighbor in node dot neighbors, what we are going to do, if so firstly what we need to do is all the neighbors, we have to check if the neighbor are there in the new graph or not. Okay, so if neighbor not in new graph, then what we need to do, we have to create a new node for them. Okay, so new graph neighbor is basically a node, and its value going to be neighbor.well. Okay, then we have to just follow the basic DFS logic. Okay, so for any neighbor, what we are going to do, we are going to check if the neighbor is not in the visited set. Then what we are going to do, we are going to again perform the DFS on that particular neighbor node. Okay, and then we will pass all the arguments. But here one thing is missing. There were total three things that we had to do. First thing, the current neighbor that we are on, if it is not in the new neighbor, then we have to create it. So that we are doing in this step. If node is not in new graph, then create it. Okay, then we are looking at its neighbor. So for neighbor in current node neighbors, we are doing this, and we are checking if the neighbor is not in the new graph, then also create a node for the neighbor. So that is also we are doing. But the third step is missing, which is basically we have to add these newly created neighbors in the neighbor list of the current neighbor. So in the neighbor list of the current node. Okay, so these neighbors, they need to be added to the neighbor list of the current node. Okay, so how we are going to do, we are going to do node dot neighbors dot so sorry, this is graph node, because we will be creating the new nodes, and we will also be updating the neighbors for the newly created nodes in new graph only, right? We are not changing the given graph. So it's new graph node dot neighbors dot append. What we have to append, we have to append this newly created uh, neighbor node. Okay, so it can be newly created if it doesn't exist. Otherwise, if it already exists, then it can be reused. Okay, so this is it. This is just like the regular DFS uh, method. The only change is that we have to do three things, like extra things. The first one is that we have to check if the current node not exists in new graph, then create it. Okay, and the other thing that we needed to do is, if the neighbor node does not exist in the new graph, create it. Okay, so that is also created. And the last thing that we need to do, the last extra thing that we need to do is basically add neighbors for the current node in new graph. Okay, and this is the basic step that we do in the DFS. For all the neighbors that are not visited, we have to recursively call the DFS. Okay, so this was it. Let's just run this run this solution. Okay, so looks like everything is passing, so I'll just submit our solution. Okay, so this was it. What we did, we firstly checked if there is no node, then just return none. If an empty graph is given, then we have to just return none, right? And what we have to do, we have created a new graph, and it's basically a dictionary. In the dictionary, keys are going to be the references for the node from the old graph. Okay, in the old graph, the keys of the old graph are going to be the keys in the new graph. Okay, so we have visited set so that we do not revisit a particular node, and then we call the DFS. In our modified DFS, if you know, this is the basic step. Firstly, we check if there is no node, then just return. Okay, then we mark the current node as visited. Okay, and then what we do is this is one extra step that we are doing. Okay, so which is basically if the node does not exist in the new graph. We know that this node exists in the old graph because we are traversing in the old graph, but if this particular node, this key which is also the key from the old graph, the same key, if does not exist in the new graph, then what we have to do, we have to basically create a value corresponding to this key, which is a node with the newly created node with the same value. Okay, so the current node that we are on is what we are creating in the new graph if it doesn't exist already. Then we are going through all of its neighbors. Okay, so when we are going through its neighbors, we have to also make sure that the neighbor nodes, they are there in the new graph. Okay, if they are not there, then we are also creating these neighbor nodes. Okay, finally, we know that the current node is there in the new graph, and we also know that the neighbor node is also there in the new graph. So we are just adding the neighbor node reference in the new graph for the current node neighbors. Okay, so the neighbor of the current node in the new graph, they are updated. Okay, and then this is the classical step of checking that if the neighbor is not in visited, then recursively call the DFS. So this was it.